Good evening, everyone. My name is Maria. I'm a coach of Siemens City ITP team. Soon we will get our presentation on the slides. I would like to thank you. I would like to present to you our team, our two customers, Jochen Niklas and Dr. Markus Zaua, our project leader, Andreas, our 6 developers, Alina, Anil, Dimitri, Flo, Florian, and Mikola. We have, over the past 2 months, developed a Simoji. That is an application that uses emojis to represent the status of industrial Siemens IoT devices. Now I pass the stage to Alina, and she will tell you more about it.
Welcome, everyone. Let's start with a brief introduction to our problem. So this is Joe. He's a Siemens technician, and he started today. He is supposed to fix issues that come up on a Siemens factory. But first, he needs to get familiar with the diverse set of devices and sensors of the production line, and this can be really time-consuming. Siemens wants us to simplify and accelerate this process. To understand our problem better and to get an idea how we're going to solve it, let's watch this trailer. So our approach is to represent current state of device with an emoji. Emoji can help us to get first quick impression of the condition of the machine we are looking at. But for that, we first need to detect and identify IoT device and read its measurement data. The system must accommodate new types of sensors and devices in future. And finally, it needs to be understandable and easy and fun to use for Joe and our other Siemens employees. To illustrate our problem domain further, let's take a look at our analysis object model. Joe, our user, has a camera on his phone and he wants visualization. With the help of a camera, he can identify one of IoT devices in production line, and all of these devices has multiple kinds of sensors. These sensors emit data that need to be analyzed and interpreted for visualization. Interpreter can use a simple threshold model or more advanced models for different use cases. Interpreted data can be visualized with emoji for simplicity and with a graph for more sophisticated representation of data. And all of visualizations are shown on the camera view with augmented reality. Now, to show you more real-life scenario, we will take a look what's going on the LS-1 Brugge spaceship.
So, Dimitri, live on this spacecraft, your new work, how do you like it?
Yeah, it is so cool, so futuristic, but the captain, he's driving me crazy all the time, yeah.
Let me tell you, it'll get better over time.
I hope so. Oh.
Bridge to engine room. We have a problem in sectors 28 and 9. Copy.
Copy that, Captain.
Listen up. You must fix it in 10 minutes. My commander has told me that it needs to be fixed before the lunch break, so I need you to get off your ass and get it done. That's an order.
I told you something would come up.
In 10 minutes? It's just impossible, Captain.
So stop complaining, Dimitri, and get to work.
Okay, come on, let's just do this.
Yeah, let's do it.
So, I have this super cool new app here that really should make this a piece of cake. So let me just fire it up here. It will just take a brief moment to initialize and get an awareness of the room, as we have seen many times today. Okay, this seems to be a very weird room. Okay, so let's have a look at the first device. This one, it's the warp drive, very interesting. So what's going on with that one? 120 megakelvin, that's very hot, even for a warp drive. So, computer, can you please check the cooling on the warp drive?
Checking cooling. Cooling seems to be malfunctioning. Fixing.
Okay, let's see if that fix actually helps and like, okay, the temperature seems to drop, very good. Let's just wait a second until it's back to normal range. That looks very good. Let's take a look at the next device. The flux capacitor, interesting. What's going on here? 120 terawatts of power usage, that's a bit much. So, computer, can you please check the preferences on the flux capacitor?
Looks like someone is trying to travel to year 1200.
That's a bit early, I think that won't work. Computer, set the flux capacitor to 1960.
Okay, set.
Okay, let's see. Doesn't seem to work. Come on. Perfect, we are back to 60 terawatts, that's okay for a flux capacitor. So both of my devices are okay. Dimitri, what's going on with you?
Hey, I'm still trying to set up my diagnostic tools.
Okay, let me take a quick look. The tractor beam, interesting. Oh, that doesn't look too good. You seem to have some network issue. But that shouldn't take too long to fix.
Yeah, I hope so.
See you at lunch, man.
See ya.
Bye.
Oh, come on.
Now to explain our system architecture, let's take a look on our top-level design. So we have different kinds of sensors that are connected to the IoT device. IoT device gets real-time data from all its sensors, and then all IoT devices in the production line send their data to the fog nodes. Fog computing enables us to gather data in real time and to aggregate it for historical analysis. Fog nodes in fog layer serves as a proxy to the cloud, where complete history of data is stored. The phone, iPhone in our case, detects and identifies IoT device with its camera, and then receives data from the fog node for real-time visualizations. And if user wants to take a look at historical data, he gets it from the cloud through the fog node. Now Mikola will tell you more about technical aspects of our project.
Okay, so we have our IoT device, which runs Linux, and this makes our system really flexible, as we can run any software basically directly on our IoT device. It also has sensor drivers which collect data from sensors, and then producer, using a lightweight MQTT protocol, sends it to the driver, to the broker, on the fog node. Broker is responsible for all the filtering and sending data through the network. Of course, after that, our Simoji app, which visually detects the IoT device, connects to the broker on the fog node and subscribes to the live data which is streamed from the IoT device. We also wanted to store historical data. So we have a data accumulator on the fog node, which caches all the live stream data and then sends it to the historical data server, which then saves it to the database. Okay, so for our problem, we have to implement the visual detection of our device. So we use machine learning. For our case, the model called Tiny Yellow version 2 was the most suitable. It's really small and simple, and it really runs fast on the mobile devices. After that, we had to create our own data set with our device. So we took some photos from different perspectives, different backgrounds, and different lightings. And of course, after that, all those photos had to be labeled. So, and it's not that interesting task, and it took us a while. After that, things got a little bit more interesting. So we trained our model with our dataset on a GPU for about 8 hours. And the model Tiny Yellow version 2 performs on a mobile device at an average precision of about 65%. That's it for the ML model, and our current status on the project can be divided in 3 parts. which is networking, detection and identification, and visualizations and UI design. We already implemented streaming live data, so we have MSDNS, service discovery and MQTT protocol, and plan to implement historical data and getting push notifications on an iPhone. Currently, we detect our device using the QR code, but we are working on improving it with CoreML and Vision. And to get rid of QR codes completely, we plan to implement advanced identification of the device. As for visualizations, we already have graphs, emojis, and labels in augmented reality. And we are constantly, of course, working on improving our UI design. Okay, that's it for today. Thank you for your time. Does somebody have a question?
Yeah, hello everybody. Thank you very, very much for your great work and your very, very impressive presentation. I liked it very much. I'd like to know which challenges you faced while developing this app, and especially what do you think about the AR toolkit, the technology you're using? Is it mature and stable enough for industrial scenarios?
Thank you very much for your question. So the biggest challenge we seem to face was that ARKit has support for vertical plane detection, but has trouble detecting, is able to detect horizontal planes, but has trouble detecting vertical planes such as this. So in the beginning of developing our app, we had real trouble placing the emoji correctly in the Z perspective. So it was jittering and wasn't really good. We have a few workarounds that seem to have solved the problem pretty okay, but we're still working on that. So that's probably the biggest issue. And Alina, would you like to add something?
Yeah, I think also bad light condition on the factories can be the problem, but I think it will be better with the future releases.
Thank you very much.